going to be using most often in this class, and that is addition of vectors algebraically. So let's review a couple of things that you probably know from math class already. The vector that we have here is 6.7 meters long. It's making an angle of 63.4 degrees with the positive x-axis, and here we're saying that one block is equal to 1 meter. Now if we look at that vector, we can draw a projection of it as if it was a ray onto the x-axis and onto the y-axis here. The projection on the x-axis tells us about how much of this vector is horizontal, and the projection onto the y-axis tells us how much of the vector is pointing in the vertical direction. We call these components. The horizontal part of the vector is a horizontal component. The vertical part of the vector is called the vertical component. We use trigonometry to determine the lengths of those components. Labeling the hypotenuse, r, we label the legs of this right triangle rx and ry. They represent the components. We can use cosine of the angle to find the length of rx. And we can use sine to find the length of ry. We can also do this with unit vector notation. The x component of the vector is r times cosine theta, and we label that ri with a little hat on the top. Now in the previous lecture, you saw the same thing drawn like this. They are equivalent to the I with the little hat, we call that I hat, and the J with the little hat, we call that J hat. Those are representations of unit vectors. And then the y component, which is r times sine of theta, is just r times J hat. If you did the previous calculation, you should have come up with an answer of 3 for the x component. So we're going to label that positive 3 I hat meters. Likewise, if you did the calculation for the y component, you should have found that the answer was positive 6 or positive 6 J hat meters. So let's try to find a resultant algebraically using the methods that were described. Let's say that you have your car, it's stuck in a ditch, you want to apply some forces to it to pull it out. These are the forces that you apply. A force of 4 newtons south, a force of 3 newtons east, and another force of 7 newtons at 250 degrees. We want to find the resultant force acting on that car. So what we want to do first is convert the vectors into components. So we're going to use the unit vector method for doing this. And 4 newtons south, if we use again an xy coordinate system, is broken down into the components 0 I hat plus negative 4 J hat. If you were to look at this graphically, 4 newtons pointing south points directly downward along the y-axis, and there's no component along the x-axis. 3 newtons to the east, we would label 3I plus 0 J hat newtons. Eastward, the vector would be pointing this way. And I'm doing this to give you a sense of what this would look like graphically. Finally, a vector that's 7 newtons at 250 degrees will be represented in unit vector form as 7 times cosine 250 degrees I hat plus 7 times sine 250 degrees J hat. And I'll try to draw that here. It may be a little bit strange looking, but my vector would look something like this if I were to add it to the second vector. That. Now, of course, we're not going to be calculating this graphically. We are going to use algebra to add these up. We add the components. We add all the I hats together and all the J hats together. Okay, so if we add everything that had an I hat next to it, we would get 0.61 I hat newtons. And if we added all the j hats together, we would get negative 11 j hat newtons. So what would this look like? Well, if we were to draw this graphically, this is our x component, and this is our y component. Our x component would be 0.61 newtons along the x-axis, a really, really small vector like that. 11 newtons below the y-axis would be negative 11 j newtons, so it would be pointing downward like that. Now this is a rough estimate, this is not exact. And then my resultant we would draw from the tail of the first vector to the tip of our y component, and this is our resultant force. Here's our y, and this is our x, like so. So the resultant in unit vector notation form would look like this. This is how we would express it. 0.61 I hat minus 11 j hat newtons. Now, of course, in the end, we really want a number. Now, this is where we start to use some math. So, as I showed you in the last slide, if we were to draw those components, we'd have 0.61 newtons along the x-axis in the positive direction, and then 11 newtons downward along the y-axis. Of course, this is not to scale. And then our resultant force is drawn as a vector that looks like the hypotenuse of a right triangle, and that's our resultant R. Now, if we look at this, we can recognize that this is in fact a right triangle, and we can use the Pythagorean theorem to solve for the resultant. So our resultant will just be the square root of our y squared plus our x squared, or the square root of negative 11 newtons squared plus 0.61 newtons, also squared, which is about 11 newtons. This is the magnitude of the resultant. It's the magnitude of the force that results from adding all those other forces together. The next thing we want to find is the direction. Now what I'm going to do is use inverse tangent to find this little angle here. We'll call that theta. And theta is just the inverse tangent of our y over our x. Theta is the inverse tangent of negative 11 divided by 0.61. And the answer to that is negative 87 degrees. And here that means 87 degrees below the x-axis. Now in general, I like to express this as an angle with respect to the positive x-axis. So what I would do is take 360 and subtract 87 degrees from this. But for our purposes, if we can locate this angle, we know which axis it's found with respect to, we can pretty accurately tell the direction of the resultant vector. So to summarize, these are the steps for adding vectors. Break the vectors into components using vector notation. Add unit vectors along each axis. Redraw the unit vectors on a coordinate system. Use the correct tip-to-tail method so that you don't get the wrong answer. And pay attention to what quadrant you're in. Depending on what quadrant you're in, that negative 87 degrees could have basically led to a different result. Use the Pythagorean theorem to find your resultant, find the magnitude of the resultant, and then use the inverse tangent function to find the direction of your resultant with respect to the positive x-axis. There's several applications of using vectors. Some of the ones that we'll be looking at to begin the course are projectile motion. We can resolve velocity vectors into the components to predict where something's going to land and how long it takes to land. And as you saw, forces, usually you have multiple forces acting on an object, so we can use this vector addition method to figure out the total sum of all of the forces. And of course, you will have to resolve vectors into components throughout the year. This ends the second lecture on vectors. Thank you for watching. Stay tuned for the kinematics lectures coming up.